Good morning, everyone. Today we continue our discussion on time series. We already know what a time series is, and we said that many of the data in finance and economics are all in the form of time series. So the one of the objective of this course is for us to be able to, given a particular time series, we should be able to come up with a model so that we can explain the time series better. We can uh, see its behavior and also forecast. Forecasting time series is a very important activity in finance or in economics. So for time series, one of the best method is what we call the Box-Jenkins approach. Okay, the Box-Jenkins approach uses what we call the ARIMA process, a autoregressive integrated moving average. The past few sessions, we have defined what an ARIMA process is. Autoregressive, which we said last time, we model the time series based on its past values. So it's like an endogenous model because you're using the time series itself, albeit you're using the lag values of your time series. On the other hand, MA makes use of the past error terms. Integrated from the ARIMA means you have to difference the data. We studied this last time. We said that the process of integration or differencing the data will heal the trend. If the data has a trend, we said that we can use ARIMA model for that. The data has to be stationary, and by stationary we mean stationary in constant in mean and constant in variance. Okay, and we said that the equation for an AR1 process is y sub t is your time series. It's equal to a certain constant. Normally, your text, or if you read some text, they will be using here a phi. Okay, so let me just uh, annotate this a bit. Okay, so this is phi null. Sorry, and let me write here phi sub null plus. Okay, apologies for the crude writing because I'm using my mouse. I ordered a digital pen for the one that I lost. Okay, phi sub 1 times y sub t minus 1 and plus a certain error term epsilon sub t. So this is your AR1 process. Okay, so this is y sub t. Y sub t is your time series, and you can model it using uh, okay the past values of itself. So that's why it's called autoregressive lag one. Lag one because we're just using the past the most past value of the time series itself. So we have this intercept, we have this constant plus a certain error term. Now, why do we put an error term? Because the y sub t, the actual or the observed value, will not be equal to, in most instances, it will not be equal to the predicted value. This is the forecast value, this is the predicted value. So in order to equate them, we have to add this residual, the difference between your observed or actual value and your model value or predicted value. Okay. And then we said that the epsilon sub t is a white noise. Okay, we defined what a white noise is last time. Okay, constant mean, constant variance. So that's what we mean by white noise. The error class, the epsilon sub t, cannot have a trend. Okay, so if you look at your residuals and it still has a trend, it's going up or it's going down, or the variance is not constant. Okay, it's ballooning, it's fanning out or fanning in. Okay, this is the behavior of your series, fanning in or fanning out then your model is insufficient. Okay, the error term here should be white noise, and we described what white noise is last time. Okay, so now kindly run this class. Press enter. And does it run in your case, this one, this LaTeX? Kindly chat, please, yes or no, because I'm once again having problem with my LaTeX. Does it run, class? Good. Oh, good in your case. No, I'm having problem in my case, so it's not running. Okay, what you will see here, class, is a okay, so in your case, yes, good for you, good for you. So if you click enter here, you should see y sub t in good format. Okay, we can put this as okay. Alpha sub o is okay. Alpha sub o, which is the symbol for your intercept or for your constant, plus phi sub I, then multiplied by yt sub t minus 1, and then your epsilon sub t, okay, which is the same as above, only that this is written in a good format. So that's your AR1 process, and we discussed that last time. Now, we also discussed the random walk. So just as an addition, plus the random walk, we said, okay, not constant mean, not constant variance, it's meandering, okay? It's unpredictable. And the equation, class, is like this, okay? Y sub t, okay, in fact, you can, let's just copy this, Control C, Control V, and let's replace this y sub t is equal to, we remove this, class. So this is now y sub t minus underscore minus 1 and epsilon sub t. All right. So this is a random walk, class. Take a look at the difference between a random walk and an AR1 process because they almost look the same. An AR1 process has an intercept, okay, while an AR1 process also has this coefficient, okay, phi sub 1. And phi sub 1 is a value less than 1. Okay, on the other hand, this one, your time series is equal to a certain, your previous value, okay? Your previous value, y sub t minus 1, plus a certain error term. You notice there is no constant here. It's exactly your previous value plus a certain random noise, okay? All right, so that's the difference between an AR1 process and a random walk. Take a look at the equation. Okay, so we also discussed what an AR2 process is last time. An AR2 process will simply have two lags. Okay, we have y sub t minus 1 and y sub t minus 2. Okay, so if you run this, okay, again, it's not running in my case, I'm sorry. Okay, so y sub t is equal to your constant plus this is the parameter for your first lag, phi 1. This is the parameter for your phi 2, lag 2. So this is y sub t minus 2 plus again your epsilon, your residual. Okay, so in general, okay, we can generalize this now. An ARP process, autoregressive process of lag p, will be equal to, so this is your y sub t, it will be equal to your constant plus phi 1, phi 2, phi 3 plus, okay, whatever the order of your AR process is, t minus p. So t minus 1, t minus 2, t minus 3, t minus 4, etc. up to t minus p, which is your p. Okay? And then multiply that by your y, t minus p, plus your epsilon. Okay? Once again, if you run that, see here the dot, dot, dot. Okay, you're adding your parameters based on the lag. Okay, I'll pause for a while and ask for comments, feedbacks. Are you able to follow so far? AR1, AR2, AR3, it doesn't matter. ARP, that's the general formula. So this could be 1, this could be 2, etc. So waiting for your feedback, class, if you're getting it so far. Feedback, please, class. You're getting the AR process, autoregressive process. You're modeling your time series based on its past values. Thank you. Waiting for the comments of others. Any questions? Any clarifications? Okay. Okay, good. Thank you. Thank you, everyone. All right. So let's now go to the other one, the MA process, because you have ARIMA or ARMA. Okay. The MA process is your moving average. So this is your moving average. And the model is you model the residuals, past residuals. So in this case, you have alpha null plus this is your residual plus theta underscore 1 times epsilon t minus 1. So this is an MA1 process because it's based on log 1 of its residuals. Okay, this one, epsilon t minus 1. Okay, so for AR process, you're using y sub t minus 1. For an MA process, you're using epsilon. You're using the past error terms. And of course, you still have to include the current residual. So in general, it will be an MAQ, and an MAQ will look like, all right, it's not here, but we can copy this. But okay, anyway, let's write the MAQ. Control C, and yeah, I think I left this as an exercise. Control V, okay, and what do we replace here? We replace here the, okay, you can highlight this and Control F. So here, what are we replacing? Let's replace all phi. Okay, all phi for shortcut class. All phi underscore okay, just this one. All phi underscore with theta underscore. So let's do that first. Here, phi with theta. Replace all. Oops, sorry, I wasn't able to highlight here. Phi theta replace all. Oops, y0. Not reading. Okay, anyway, sorry about that, class. Just have to replace this manually. I'm sorry, it's not theta. So this is theta 1, and then you have to replace this with, okay, this is longer, epsilon. theta, and then epsilon. So it's like this class. Okay. Let me just copy this. Control C. Replace this. Oops. Control C. Let me replace first the phi. Control V. Theta didn't copy. Control C. Control V. Okay. And then theta 1, epsilon, theta 2. I'm going to replace my y, control C, with epsilon, control V. All my y's with epsilon, control V. And usually in MA, epsilon, we put this in front. Control X, put here. Okay, so sorry for that exercise. Okay, so you should be able to print the MAQ process. So you have your constant, and then you have your epsilon, epsilon sub t, the error at current time, plus the error, the residual, the previous period, the residual of past two periods, 3 periods, and p. So this should be t minus q. Sorry, t minus q, because an MA process is an t minus q, t minus q. All right, I'll give you a few seconds, class, to write. So practice in writing the equation. And again, I'll be asking for your feedback. If you're okay, express yes. If you're able to write, and please have the equation printed and see if it's okay. I'm sorry, my R is not working properly. But wait, what did we just do here? We replaced the coefficient phi with theta, just to uh, make it uniform with most of the text. For most of the text, they use the theta Greek letter to denote the moving average. Okay, thank you, Kate. Let's wait for the others. Okay, Sam, thank you. Okay, Adam, Regine, Angeline, okay, Kushan, Katrina, acknowledging your post. Danica, thank you. Jay, thank you. Okay, a few more seconds for the others. So you notice that in the MA, we usually write epsilon, the current epsilon, epsilon sub t first, followed by the epsilons of the previous period. Unlike in an AR process, you write the epsilon last. Okay, thank you so much for your feedback. So if we have a combination class, an ARMA 1-1 process will mean this will be for your AR, this will be for your MA. So we have this one, technically this is, so let me write this. So this is your alpha null, right? Your constant. And then you have for your AR1 process, the one here class refers to your AR process, and the one here refers to your MA process. So this is actually ARMA PQ. Okay, P stands for the log of your AR process, and Q stands for the log of your MA process. So ARMA PQ combines, okay, the log 1 of your AR process and the log 1 of your MA process. Okay, so this is autoregressive moving average 1, 1. Why 1, 1? Because log 1 for AR process, log 1 for MA process. And you notice how epsilon sub t is written at the start of your residuals. Okay, so you can write it this way, class. Unfortunately, mine is not working, so okay, can be written this way. What's this? Alpha sub 0, epsilon sub t. So this is this is what's this class? This is your MA1 process. Okay, I don't know why it's there. All right, so as we said last time, okay, ARMA PQ and then ARIMA PDQ. Okay, so notice I inserted I here to account for the D here. So actually you can write this as ARIMA PDQ. Okay, and if there's no differencing, we'll have ARIMA P and then 0 and then Q. Right? Assuming there's no difference, there's no differencing. Okay, we studied differencing last time when we subtract your data depending on how many differencing you're getting. All right, so this one we discussed last time, okay? And we said that in order for us to use the Box-Jenkins approach, we have to make sure that your time series is stationary, okay? Plot the data, so these are the steps, class, the Box-Jenkins approach. Plot the data as time series and check if stationary. If it's not stationary, class, again, by way of review, what does it mean to be stationary? To be non-stationary. To be non-stationary, okay, you have your data, this data, for example. Okay, sorry for the very good drawing. Okay, so this is an example of a non-stationary data, not stationary. Why? Number one, it has a trend, okay? It's going up. So if your data is going up or it's going down, that means it has a trend. Then that violates the principle of stationarity. Secondly, albeit a bit crudely, okay, your variance is not the same. Okay, so your variance is not the same. It's like having a, for example, like this one. It's fanning out, which means over time the variance is increasing. The variance is not constant. Okay, so in this case, your data is not stationary. And as I reminded you before, when you say stationarity, it should be stationarity in both constant mean and constant variance. Constant mean, MEAN, means that the average does not fluctuate, okay, across time. So you may have this time series. Okay. This is a time series. I'm sorry about this. This is a time series which has constant mean. Okay. If you take a look at the average of the mean, anywhere, any portion you have here, it's practically the same. Okay. To get this period, the mean is here. To get this period, the mean is here. If you get this period, the mean is here. It's so the average mean is constant, and also for stationarity in mean and also variance. What do you mean by constant invariance? The data, the time series does not fan out. If your data is going this way, it means non-constant variance because the variance is increasing over time. Okay. So if you have non-constant variance, and even if the mean is constant, in this case, the mean is constant. Even if you have fluctuations here, if you get the average here, it will be the same. Okay. So the mean here is constant, but the variance is not. So even if the mean is constant and but the variance is not, then the data is not stationary. For the data to be stationary, it has to be constant in mean and in variance. Okay, so how do we treat the data? If we want to use ARIMA process, how do we transform the data so that we can use ARIMA? Okay, number one, if the data has trend, then what you do is get the trend by treating it with differencing. So you difference class. Okay, if you difference the data, then most likely it will have a constant mean. It will remove the trend. Sometimes you need to do double differencing. When you say double differencing, you difference first and then you difference again in order to make the data stationary in mean. Okay? Now, how about the non-constant variance? The non-constant variance calls for us to there are different ways to do this. There are different ways to transform your data. One of the most popular one is log transformation. Okay, so you first get the log of the data, so that any non-constancy in variance will be treated. It will be made into a stationary or constant in variance. Now, what happens if you have both non-constant variance and a trend? We learned last time that what process do we have to do? Do we difference first and get the log? Or do we log first and get the difference? Kindly chat, please. LD or DL? LD stands for, this will be the first one. This will be the second one. Get the difference first and then get the log, or get the log first and then get the difference. Which will it be, class? Write 1 or 2. Is it step 1 or step 2? Step 1 is getting the difference and then get the log. Step 2 is get the log first and then get the difference. Is it step 1 or step 2, class? Which is the proper order of transformation? Okay, 1, 1, 1, 1, 1, 1. Okay, the answer, class, is 2. Okay, you forgot easily. When you get the difference first, okay, and then get the log, class, there will be this there will be a discontinuity in your data. Because when you get the difference, most likely you'll have a negative answer. And you cannot get the log of a negative answer. Okay. So what do you do first, class? Get the log and then get the difference. Okay. There will be no problem if you get the log, class, and then get the difference. No problem with the uh with with your time series. Okay, did that answer your question, class? Because if you get the difference, you'll have negative answers. So of course, I'm assuming here that your data are the prices. They do not contain negative numbers. So you can get the log of that data. If on the other hand, you're dealing with returns, and returns class will have, if you're already dealing with log returns class, so that means you already got the log of the data. Okay, you got the log of the prices. Then you have actually effectively done this already. You've gotten the log, so the only difference. This will become clearer as we have an example. Okay, any questions so far, class? Any questions so far? Are we clear? Feedback, please. Thank you. Okay, good. All right, then, okay, after you have done the transformation, you got the log and then you got the difference, you plot the data again and check if the data is stationary. Okay, so how do we check if it's stationary? Can be visual, but there are also some statistical tests which we're going to use in order to statistically prove that the mean is constant and the variance is constant. So some of the examples are ADF test, KPSS test. ADF stands for Augmented Dickey-Fuller. Augmented Dickey-Fuller test. So these are statistical tests used to determine if the data is stationary or not. Okay. Then step 6, you plot the ACF, it's called the autocorrelation function, and the PACF partial autocorrelation function. Now, what's the use of that? What's the use of that? It will help us identify whether you have an AR process, an MA process, or an ARMA process. So this is the purpose of this one. Step 6 allows us to evaluate and uh, and uh, perhaps uh, guess. I think that's the proper word. Guess if the series is AR or MA, or it needs some more differencing. All right. Then after that, after we have identified the model, we check. We run the model and check if it's the best model. Then, of course, if it's already the best model, then we can now forecast the time series. Okay. And of course, last step is also to check the residuals. We will have to check and evaluate the model for residuals. Okay. Actually, I'm sorry about this. Um, okay. Sorry for the wrong order here. step 8, kindly just modify. Okay, because you only forecast if the model is already valid. If the model is not valid, then you do not forecast. Yeah, you'll have to change the model and make it and analyze the residuals. Okay, and the residuals should be, what should the residuals be, class, for your ARIMA, for your ARMA model? How should we describe the residuals? So we have a model, we have the observed value, actual value, we have the predicted or model value. If you compare the actual value with the predicted value, and then you plot that, let's say your residuals, they should behave as what, class? Anyone? Should be white noise. Okay, we said a while ago. The residual should be white noise. I mean, it should behave as if no, there should be constant mean and constant variance. If the residuals do not behave that way, then the model is not good. Okay, so that's why it's very important, this one. Let me write this. Residual should be white noise. Okay. All right. Okay. So this is just a review, class, of what a stationary time series is. We said that the mean, variance, autocorrelation are all constant over time. Okay, they do not change over time. So a stationary data time series will look like flat. By flat, we mean there's no trend and there's no fanning out or fanning in. Okay, constant mean, in the implication of which there will be no trend, and constant variance, which means that the time series will not be fanning out or fanning in. Okay, so these are just some notes. Okay, maybe let's take a look at this. Okay, could you kindly copy this? Control C. Okay, and let's take a look at this site. This is a good reference. Okay, so this is from O'Reilly. Talks about stationarity of a time series model. All right, this is a stationary time series, class. Stationary time series, no trend, constant variance. Okay. So last time we looked into this is a non-stationary time series. Okay. In fact, it looks like a random walk. Okay. There is a trend. Okay. And the variance is not constant. Right. So I just wanted to show you the diagram. Okay. So let me close this and let's go back to our code. Okay. There are some other examples here. Maybe you'd like to, let's copy this. Control C. And this one also illustrates the stationary time series. Okay, here. Same thing as the site a while ago. And here, class. Stationary mean, stationary variance. You have here, the mean is not stationary because it's increasing over time and it also went down. But the variance is stationary. There's no fanning out. Okay. On the other hand, this one, the mean is stationary. There is no trend, but the variance is not stationary. It's not constant. It's decreasing over time, the fluctuations. Okay. So this is an example of a fanning in, fan, F-A-N-N-I-N-G. fanning in. All right, so just wanted to show you that as an example of a stationary time series in mean and variance. Then you have your, the mean is not stationary, but the variance is. Then you can also have the variance is stationary, but the mean stationary, but the variance is not. Okay, so going back to our, okay, so here class, white noise, okay? It does not matter when you observe it. It should look much the same at any point in time. All right, so the time plots will show to be roughly horizontal, although there might be some aberrations in some specific points in time, but that should be more of the exception. And the variance should be constant. All right. So we said here that a stationarized series is relatively easy to predict. Okay. So why is it important that we transform our data into a stationary time series? Simply because when the data is already stationarized, it will be easier to create a model out of it. So that's one of the main reasons why in the ARIMA process, there's a requirement that your data should be stationary. Why? For purposes of creating your model, it it facilitates the creation of the model, okay, whether it's AR or MA. Okay, so what will happen if your data has been converted, has been transformed? For example, you 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 got the log of the data, and then you got the difference. So what will happen is that you now have a different data. It's not the same as the original one because you have transformed your data. It doesn't matter. So you can model now the transformed data, and then later on you can revert back to the original original time series. So that will not be a problem. It's easy to do that. Okay. So we did this last time. So quickly, let's since I already gave you the code, so there should be no problem running this. So this one first. Again, we're using air passengers here. And then we generated this object called AP to represent air passengers. And then let's take a look at the first. So let me just highlight the first two. And you can see here are air passengers. Our air passengers. Okay, let me delete this and go back here. So let me run air passengers and view it. Okay. So this is a vector, okay, time series vector. And let's create AP. Let's view it also. It will be the same as air passengers. Control Enter. And it will print, so here AP, air passengers, they're the same. And let's have the first 24 observations printed. So this is the first 24 observations of our data. Okay, so we can now move on class faster with the code because you already have it. So we can get the structure, okay? And for the structure, we'll be informed about what type of data this is. This is a time series data, 1 up to 144. This is a vector class. Okay, a vector is a set of numbers, a set of data that have the same, that are of the same type. Okay, we did this last time class. The frequency is 12, which means this is monthly. The cycle, okay, this one class, right? This is the cycle of your data. So from 1949, okay, 12 observations for 1949 until 1960. All in all, that's 12 times 12, that's 144. Okay. So tail will just give us the last 24 observations. I'll not run that. And summary will give us the 6 number summaries. Since it's only one, you only have 144 numbers. You can get the minimum, the maximum, the first quartile, second quartile, third quartile, and also the mean. So the average is 280.3, the median is 265.5, telling us that the mean is towards the right of the median. So medyo right skewed tong data natin. No? All right. So for this one, we also did this last time. We plotted AP. Okay. We placed a label for the x-axis, y-axis label also, and then the main plot, and then we print P1. So let's run this. Okay, so this is our plot. We have a name for the y-axis, passenger numbers. We have a name for the x-axis, your date, and this is your plot of the data, and this is the main air passengers from 1949 to 1960. Okay. All right, let me pause for a while and ask you if you're able to follow. I think the advantage of giving you most of the code is that we are able to quickly discuss. There's of course a disadvantage because there will be a tendency for you to have less practice in writing the code. Okay, feedback please if so far you're able to follow. Okay, good. Thank you. Okay, thank you so much. All right. Thank you. I hope everyone is able to follow. Okay, we can also use, there's a function. We already loaded this GG45. GG45 has this autoplot function. It will be almost the same as the above. It will only differ in features. Okay. Oops, sorry. Autoplot, why? Let me just check. Autoplot. Did it run in your case class? What's the package for this one? May I have your feedback, please? If it ran in your case? All right, where is that? Forecast, yeah. Forecast. In your case class, did it run? Yeah, good, good. Thank you. Which means I haven't run. I didn't run the packages. Forecast, let me run. Okay. All right, so forecast has already run. So let me just, where are we now? We're here. Okay, we should run now. Still error? Error in, huh? Could not find labs. Labs is, okay, it must be coming from another. Okay, let me just, sorry class, let me just run the, I forgot to run this code chunk. Okay. All right, so it's now running. Okay. So this is another example where I did not run the packages. Okay. So I hope this runs now. If it doesn't, then I'll just have to check. There you go. Okay. So it's just the same class as the plot function, only that the autoplot is cleaner, okay? And it has advantages, especially if what you're plotting is more complex. All right, then let's just have this one we did not run last time, but the cycle we did, this one class. So let's plot our data. Okay, this is very useful class for descriptive statistics. Let's use the box plot, okay, AP object, and then we have to cycle it, which means we have to convert it into uh, all the ones, all the twos, all the threes, all up to all the 12. Okay, so let's run this. Our box plot one. Okay, and it will give us a box plot. There you go. So this is all the ones. Now, when we cycled class, when we use the cycle function, okay, take a look here. Going back here, cycle. What does this give us? Okay, it gave a number. All Januaries are 1. All Decembers are 12. There, that's what the cycle function does. So when we use that here in the box plot, all the number ones here are January, okay, for all the years, 1949 to 1960. All the 12s here are December. So we can look at this and say that it is every July where you have a bigger volume of passengers, right? Okay, a bigger volume. This is your median. This is your median. This is your maximum. This is your minimum. So you can see the some information about the distribution of the data. You can see that the lowest in terms of minimum is November here. Okay, the highest in terms of number of air passengers is July, followed by August, as far as the distribution is concerned. Okay, so this is when you're doing a paper, for example, and you need to describe your data, this comes in very handy because it's a very good visual display of how the different months behave in this case. Okay, and then I have here some notes just for additional discussion. Okay, I leave you class to discuss this. Okay, to read through it. Okay, so in fact, we said last time that air passengers appears to be multiplicative time series because the variation of your data seems to be increasing. Okay, and there are no outliers. You can see outliers if there are points here. Okay, points above this whisker. Okay, so if you have, for example, if in this plot, you have points here, for example, here, or below here. So this will be your outliers. In this case, no outliers can be seen. Okay, so let's okay. So about this class, what we do here now is from the stats package, let's decompose the data, the object, AP, air passengers. So we know that there is what do you call this? Sorry. There's trend and there's seasonality. Sorry about that. There's seasonality. So we said last time that seasonality can be additive or it can be multiplicative. AP seems to be AP. No, sorry, plot. Once again, AP. Take a look at this. There. Plot AP. And the seasonality seems to be, okay, it seems to be multiplicative because it's increasing over time. Okay, so we can actually decompose this AP using the decompose function here. You have this class. So I'm creating this object decompose AP and additive. I'm assuming it's additive. So we're using the stats package and we use a decompose function. Okay, so this is very powerful. It now will break down your data into a trend, into seasonality, and into a irregular or a random. And we'll assume that this is additive. When your data is assumed to be additive, then the equation is the time series is equal to the trend, the seasonality, and some random term, right? So let's run this. Run this first. The first, okay. So we now have this okay. It's not showing here. Okay, I'll just run the whole code chunk class. Okay, so it will show also here. Okay, take a look at this class. So this is your data. So the decompose function will split your data into the trend. So this is the trend. This is the seasonality. Again, you notice the peaks and troughs, the peaks and the troughs here. And then this is your random component. So your random component is not part of your trend, neither is it part of your seasonality. So in this case, it's a difference between your actual value, okay, minus your seasonal component minus your trend component. That's that's the remainder. Okay, so that's what happens when you decompose your data. Now we can also decompose it and assume it's multiplicative seasonality. For multiplicative class, the equation is like this. If we draft the equation for multiplicative, it will be y sub t is equal to your trend multiplied by your seasonality multiplied by your random term. So let's create this object, mult. Okay, decompose again, and the assumption it's multiplicative. Okay, run. All right. Okay, so you will not really see much of the difference. You will see that when you create the model itself. Okay, but here you were able to break down the trend, and the seasonality does not seem to be that much multiplicative. Okay, it doesn't. Although there may be signs of increasing, but not that much class. We were assuming it's multiplicative. All right. Any questions so far, class? Again, chat, please. We have time more to to just discuss the stationarity of the time series. Please, so far, class. And let me go to the last portion of our discussion. Okay, I hope it's clear, class. Thank you. All right, so for this one, class, this is now the test. Okay, the test that we need to have in order to determine if your time series is stationary. Okay, of course, you can look at it visually and you can say that it's stationarity or not. Some, of course, are very obvious. They're not stationary. Okay, so we're going to use from the T-series package this test called ADF.test. As I said, ADF stands for the Augmented Dickey-Fuller Test. And it's a test used to determine if your data is stationary. All right? So here, the syntax is alternative is equal to stationary, which means that the null hypothesis is that the data is not stationary. It's not stationary, as I pointed out here. K refers to the log, okay? Log of 12. Okay, if I run this class, and let's see here. Okay, augmented Dickey-Fuller test, the data is AP. You have here the Dickey-Fuller statistics. Log order is equal to 12, and p-value is equal to 0.787. 0.7807. Okay, what does this tell us? The null hypothesis is that the time series is not stationary. The p-value is 0.7807. Therefore, our conclusion is we fail to reject the null hypothesis that the time series is not stationary. Okay, so here we have a statistical test that tells us that the time series is not stationary. Okay, as a last example, class, before we go, okay, Control Alt I. If you recall, class, we created this, right? The last time, the difference log AP. Let's redo that, class. Alt minus. Okay, sorry. So it's getting the difference of the log of AP, right? Okay. We did this last time, so let's do this. Okay. So there. Let's just quickly plot DLAP. I'm doing this quickly, class, because we did this last time. Okay, it looks like stationary. However, let's now make use of this class. Let's copy this. Control C and put that here. Control V. So we're again using the augmented DQ Fuller test, but this time what we will be testing is the difference log of AP. All right. So we're changing the object that we're testing. So if I run this, Control Enter, okay, what do you have? All right, so p-value is 0.06. And the alternative hypothesis is that it's stationary. You notice here that the p-value is greater than 0.05. Okay, but it's a lot lower than 0.7807. So you might be thinking statistically, then our conclusion should be reject the null hypothesis that the data is non-stationary. Okay, so we'll continue with this next time and tell you one of the disadvantages of using the ADF dot test. Okay, mas maganda, it's better to make use of what we call here. There is this one called the KPSS test. Okay, let's copy this, class. Control C. And then I put it here. Control V. And I use again DLAP. Okay. And then run this, Control Enter. Okay. All right. So what does this tell us? Okay. Okay, it's already time. I'm sorry to extend. We'll continue with this next meeting. So far, what we have reached is that we're now doing statistical tests for our time series. Okay. And next meeting, class, we will now start with, okay, modeling this using ARIMA. We'll discuss this next meeting. Be sure to bring this. Okay, we'll see I'll meet you in class, and then let's see how I can manage my requirement to be in a particular seminar in the LSU. Okay, so let me end recording now.